Hello to everyone. Today, second day of our conference is going. So let me introduce Hongmei Hu from Suzhou University of Science and Technology. It's very nice talk. So go on.
Thank you very much. Many thanks to the organizing committee of the conference. And I also give my heartfelt thanks to Bart and his invitation. I'm so happy to have the opportunity to share our work to everyone. Please forgive me if I can't get your question well, since this is the first time for me to give a talk in English. The talk is based on joint work with Professor Chang Hao. We extend the Drinfeld-type presentation of the superalgebra associated to the general linear superalgebra GLMN and the special superalgebra to positive characteristic. Then the center of the superalgebra YMN is described. It is generated by its Harish-Chandra center together with another p-center. Also, we also study the p-center of the special superalgebra, and we also provide another description of the center of YMN in the RTT generators. So there are 4 parts in my talk. Firstly, I want to talk about some background and our motivations. Each finite dimensional Lie algebras, the corresponding Yangian is defined by Drinfeld, which is a canonical deformation of the universal envelope algebras of GLMN. Yangian is a remarkable or family of quantum groups related to rational solutions of the classic Yang-Box equations. Now, here I want to focus on explain why we study the center or the p-center of the superalgebra on over positive characteristic. A finite W algebra. A finite W algebra is defined by a pair of finite dimensional semi-simple algebra and its Lie-potato element. In the extreme case, when the Lie-potato element is 0, the corresponding file W algebra is the university envelope algebra. In the other extreme, when the Lie-potato element is principal, then related W algebra is isomorphic to the center of the university envelope algebra. Here, finite W algebras for generally Lie-potato elements is firstly developed systematically by Professor Primate in this paper. Now we have Yangians and W algebras Then, are there any relation between them? Yes. The collections between Yangian and W algebras is firstly latest by Rogesi and Saber for type A Lie algebra. Then observation is falsely generalized by Brander and Krashev in these articles in these articles. Now their result can be described shortly as follows. A finally W algebra is isomorphic to a quotient of some subalgebra of shifted Yangian for type A Lie algebra. Then Brander, Goodwin, and Topley extend these results to positive characteristics in these papers. Here a passenger appears in a natural way, and it plays an important role in their results. Then the supervisions of W algebras appears their finally W superalgebras. Finally W superalgebras are defined in a very similar way as the Lie algebra case, except that the real potato element is assumed to be even. And then super Yangian is defined by Nazova. So it is so it is natural to seek for the collections between 5 W superalgebras and super Yangians. There have been some results. In recent years, there have been some results for the real potato animals satisfy some conditions, but for a generally real potato animals, Professor Peng Yongning give a solution to this problem in his paper. Here are our motivations. We want to extend Peng's works to positive characteristic and obtain the supervisions of Goodwin, Brand, and Topley's work. Since massive parities in characteristic P make some computations more complicated, therefore, also the method is well established in the above some papers. Such a generations is skill is by no means trivial. We want to finish our motivations step by step. Our first step is to extend extended Drinfeld-type presentation of the super-Yangian in girls' works to positive characteristic. Yeah, is to Drinfeld-type presentation of the modular super-Yangians. Of course, the collections between Yangian and W algebras provide a powerful tool study to study the W algebras, including their representations and further applications. There are many papers to demonstrate this. Now I will introduce some notations. In my talk, K always is algebraically closed field with characteristic P. P is bigger than 0. And G is the current superalgebra associated to the general linear superalgebra GOMN. Then these elements ERGXR make a basis of G, and the degree of each basis element ERGXR is divided by the parity I and J. The parity of I is 0 if I is from 1 to m. Otherwise, the parity its parity is 1 if I from m plus 1 to m plus n. In characteristic 0, in characteristic 0, it is very easily to prove that this even animals is central in the university envelope algebras of G. So the subalgebra generated by these central elements is called as Harish-Chandra central in characteristic 0. But we found these definitions and results also make sense in characteristic P. Not only this, but also in characteristic P, the current superalgebra T administers a natural structure of restricted Lie superalgebra with the P-mapper, such P-map defined on the basis in this way. Then it makes us to prove that for these even animals also belong to the central, and the subalgebra generated by these animals is called as the P-center of the university envelope algebras of G. Okay, if I equals to J, the corresponding P-center elements are also called as diagonal P-center elements. Otherwise, if I is not equal to J, we call these P-center elements often offer diagonal P-center elements. Okay, the center of this, then we can prove the center of universal envelope algebras is generated by is Harish-Chandra center, and the patient. It is it is not very difficult. Its proof is very similar to Brand and Chokde and Goodwin's work. Okay. The super Yangian associated to GLMN over the complex field was defined by Lazuva. Following Lazuva definitions, we defined the super Yangian YMN over K over a positive characteristic in this RTT formula. Here, the parity of each generator's TIGR also is divided by the parity of I and J. Notice that the left side in these relations is superly bracket. So, okay, we can give this former power series Tij mu with coefficients are generators Tijr and the matrix T mu. Then we can these above relations in our definitions can be rewritten as the following equivalent expressions in the former power series and the matrix form. This is called the RTT relation or RTT presentation. Okay, now in positive characteristic, we have defined the modular super Yangian. Also, we have the restrictor superalgebra gene. Then we can define the degree of the generator TIGR is R minus 1. Then it gives the loop filtration on the modular super Yangians. Then such assignment gives rise to the following isomorphic of graded superalgebras. When we have such isomorphism, there is a natural question: what is the inverse image of the center of the university envelope algebra? In order to answer the questions, we lead to Drinfeld-type presentation of the modular super Yangian. Okay. So I will go to the second part of my talk. First, we can, in terms of quasi-determinant, to give then make the matrix T mu have a Gauss decompositions. Each entrance in this, Di entrance is the former power series, Di mu, Eij mu, Fgi mu. Each entrance is obtained by the quasi-determinant. We use the following notations: dir, di prime r, eijr, fjr for the coefficients in this former power series. Then in terms of causative determinant, we have inductive relations. By induction way, we can get it. Okay. By multiplying out the matrix product of the Gauss decompositions, we see that each generator's TIGR can be expressed as a sum of monomers in DI mu, DIR, EIJR, in center orders that OFs before D and OD before E. But we can use these inductive relations. Then we found. We just use this element only. Then we obtained this theorem. The modular superengine YMA is generated by these elements subject only to the following relations. Okay, in order to rewrite down these relations between Drinfeld generators, we write down these complicated relations. We start with some special cases when M and N are either 1 or 2. That are relatively less complicated. Then we use some morphism, for example, the swap map, the shift map, to obtain the generally or to obtain these relations in the general case. Here, these relations highlighted in red are different from the case of characteristic 0. For example, if we set S equals to T, then the first cubic series relations can produce the third cubic series relations in characteristic 0. But we can do it in characteristic T. Alas, here we lead quartic series relations for all admissible I in our positive characteristic, but in characteristic 0, they only need one quartic series relations for I equals to M. Since the corresponding quartic series relations when I is not equal to M can be followed from other relations and cubic series relations, but we can do it in positively characteristic. So here we lead all quartic series relations for all I. Up to now, we have a Drinfeld-type presentation of the modular superengines. Then we can describe the center of its center by Drinfeld generators. First, in order to describe Harish-Chandra center of the modular superunion, we follow Nazover's definitions. We give quantum bracketing of the matrix T mu in this vase. Okay. The former power series C mu its comfort coefficients of this former power series are denoted by Ci, and we can prove that these coefficients Ci are central. Furthermore, we have that this the element Ci has degree R-1 with respect to the above loop filtrations, and the image of under the above assignment is Z-R-1. So as we know, Z-R-1 belongs to the center of the university envelope algebras of the current Lie superalgebra G. So we provide the subalgebra generated by these elements is Harish-Chandra center of YMN. Second, in order to describe the diagonal p-center elements of the modular superunion. Diagonal means I equals to J. Then we defined the former power series Bi mu, and its coefficients are denoted by BIR. Then we have under the above assignment, we have these relations, so we can prove this animal, the subject generated by these animals is the diagonal p-central elements of YMN. Next, in order to describe the off-diagonal p-central elements of the super modular union, consecutive application of the swap map and the automorphism between the modular superunion make us to obtain that all coefficients EIGR and FGIR belong to the center of the university, or belong to the center of the superunion. So now, up to now, we have diagonal p-central elements and off-diagonal p-central elements. Then we can define the p-center of the modular superunion to be the subject generator, subalgebra generated by this element. Notice that this diagonal p-central elements for the case of I equals to J, and Harish-Chandra those elements in Harish-Chandra centers is also belong to the diagonal. So maybe the intersection of them is no empty. So in order to describe the intersection of Harish-Chandra center and the diagonal p-central elements, we give a formula power series BC mu, and we can prove that its coefficients in this former power series belongs to the intersection of Harish-Chandra center and diagonal p-central elements. Yeah. So we describe the center of the modular super-Yangian YMN in the following theorem. Okay. In the last part of my work, I want to give the p-center of the special super-Yangian and provide another Drinfeld presentation of the special super-Yangian. Then we also provide another describe of the p-center of YMN in RTT generators. In the third part of my talk, the center of YMN is expressed by Drinfeld generators. In order to define the special super-Yangian, we later this automorphism. For any power series f mu, there is an automorphism mu f. Mu f is defined by this voice. Then with this automorphism mu f, we define the special super-Yangian associated to the special linear Lie superalgebras SMN as the following subalgebra of YMN. Then in order to give Drinfeld presentation of the special super-Yangian, we let the former power series Hi mu is defined by in this way. Its definitions related to di mu and its inverse. Okay. Then with the Drinfeld-type of the super-Yangian YMN, we can prove the Drinfeld presentation of the special super-Yangians in this theorem. It is not difficult, but very complicated. You should. We have the relations among di mu, eij mu, and ft mu. Then from the definition of HI mu, so we can give these relations. Okay, under this presentation of the special superengines, then we can give the p-center of, we can give its p-center. In order to do this, we defined another formal power series AI mu. Its definition is related to the former power series HI mu. Just we defined in above. Okay, then we defined the p-center of the special superengine to be the subalgebra generated by these animals. Why we give this definition? Since we can prove the following result. Under the above assignment, we can prove these subalgebras. The graded structure of these subalgebras is isomorphism to the p-center of the currently superalgebra associated to the special linear superalgebra SLMN. Then we also proved that if P cannot be divided by M minus N, then the p-center of the special superengine just is its center. There are no Harish-Chandra center. Okay. So we give the p-center of special superengine.
What if we does divide M minus N?
This. Oh.
So if it doesn't divide M minus N, it's the same as the unit center. And if it does divide M minus N, then what happens?
We don't know. But we just prove if cannot be divided by. Since we are in positive characteristic, so the conditions cannot be divided by unlated in here in positive characteristic. As we know, there is a representation of the special superengine given by Drinfeld in 1987. Is associated to the Cartan matrix. Since the Cartan matrix appears, so here we later note that the characteristic of the field is not equal to 0. Since this, okay. In order to obtain another Drinfeld presentation of the special superengine associated to the Cartan matrix, so we defined the many new formal power series by DI and EI and FI. Here mu is the is an automorphism from the superengine to superengine, defined by in these ways. In the former power series and way, this is element. This is element. How to okay. We also defined it hi plus s minus 1 by di prime and di. Then we defined three new form power series: chi, cosI plus, cosI minus. So then we give Drinfeld another presentation of the special superengine SYMA. Is generated by these animals subject only to the following relations. This relation is associated to Cardan matrices. Okay, at last we give how to describe the center of the superengine in RTT generators. In third part of my talk, we describe the center of the modular superengine by Drinfeld generators. Then here we use RTT generators. So in order to do this, for the even element, we can define the former power series Sij mu. Notice that the definition of the Sij mu is dependent on the parity of I. If the parity of I is 0, we define the Sij mu in this way. If the parity of I is 1, we define the former power series Sij mu in this way. Notice that these are Tij prime. Okay, with this we can provide the epicenter of the modular superengine is freely generated by these elements. These elements are coefficients of the former power series Sij mu. Okay, then up to now we obtained the Drinfeld-type presentation and the center of the modular superengine. Also, we describe or we provide another Drinfeld presentation of the special superengine, and also we describe the epicenter of the modular superengine in RTT generators. The next stop, we want to give a parabolic presentation of the modular superengine. And it extends the works related to shifted engine to positive characteristic. Finally, goal of our goal is to give a very good application to modular, finally W superalgebras by the modular super Yangians. Okay, that's all. I stop here. Thank you very much.
Thank you for your talk. Any questions?
The finite characteristic case is similar to quantum groups at roots of unity.
Quantum groups?
And this center that you described, I'm wondering if it has a Poisson structure.
Poisson structure?
Yeah, the structure of a Poisson algebra.
We don't consider the Poisson structure.
Okay.
We don't consider.
Okay.
Thank you.
Thank you.
Other questions?
There was a similar question yesterday. So at some point you do the Gauss decomposition.
Yeah.
Is it obvious that it can be done always straightforwardly?
This?
So is it an obvious algorithm to do the Gauss decomposition in your case?
Is it easy to prove it?
No. It's not very difficult, but much more complicated. There are some amazing parities in characteristic P make the computations much complicated, but a lot difficult.
Technical.
Chocolate.
It's like,
Other questions?
I want to follow up to this question. So I think the question is the following. If you take a matrix, then it doesn't always factorize. There is not always a Gaussian decomposition. Some minors may vanish. Algebraically, it corresponds to some ideals in this algebra generated by the minors which can vanish. Did you look into the corresponding quotient algebras? No. Okay. No, it's okay.
Sorry.
It's okay. It's just one of my favorite questions.
Anyone? So let's say thanks to our speaker.